I think Sarah is going to allow everyone in.
Yeah, are we ready? Do you want me to admit all?
I believe everyone else is.
Yeah, okay, and I'll work with Kyle. So Kyle will be late, but it's okay.
Okay, so I'm going to admit all, and then I'm going to check that unmute thing because he will not be able to unmute himself. And then someone, if they really want to make sure that people don't unmute themselves, you can go into security and change it, okay?
Okay.
Okay, I'm admitting people now.
Okay. Good afternoon, everyone. My name's Albert Pashkowiak. I'm a member of OSETT, the Kingston chapter, and the vice chair of the Young Professionals Committee with the OSETT corporate. Here today, happily here today to present to you a presentation on Transpod and Hyperloop in the Ottawa Valley region. I have with me here Thierry Bautier. And before we get to Thierry's side of things, he'll be presenting the nitty-gritty of the presentation. I'd like to just chat a little bit about OSETT prior to that, and I have a short video to share as well. So I'm going to go ahead and share my screen. Okay, can everyone see that?
Yeah.
Yeah.
Perfect. Okay, so this initial discussion is really just about what OSETT is. So again, like I said, my name is Albert Pashkowiak. I'm a certified engineering technologist and a member of the Ontario Association of Certified Engineering Technicians and Technologists. So that's OSETT. So I understand quite a few high school students are joining us today to participate. And I thought I'd just relate to you a little bit and sort of well, you know, when I was a high school student a long time ago, I didn't really know what OSETT was or really what a professional nonprofit organization was, which is exactly what OSETT is. When most of you think nonprofits, you're thinking commercials for or advertisements for donations for worthy causes. OSETT is also a worthy cause, but a little bit of a different scale. So we're an association that's known as a charity, but which is another type of association, but it's a professional association. So we represent members who work in various industries, in engineering related industries. Professional associations represent individuals working in particular professions, but for us, it's across the board. There are multiple industries that we cover, varying types of engineering. You know, it's not rocket science, but it's a concept I really wasn't aware of at your age, and perhaps it's beneficial to you. The association itself represents over 25,000 engineering technicians and technologists, and that's in 15 different disciplines of engineering technology. That's across Ontario. Most or many OSETT members start as college students, and then upon graduation, they become associate members, and where from there they usually complete their membership and become fully certified members like myself. Why do college students join OSETT? Well, I studied civil engineering at St. Lawrence College, and during my college education, I learned about OSETT and actually learned about the interactions that they have and the networking opportunities that are available as part of the organization. I decided to join after graduating, and as part of that organization, I've had countless opportunities to network with my peers and meet lots of interesting people. And also really an opportunity to influence the profession in government realm as well as the public realm. Before I go, what I'll do is I'll flip you over to a short video, and then from there we will hear from Thierry and his colleagues. One moment. Okay, here we go.
Why are you more qualified than other candidates?
Well, first, I'm OSETT certified.
OSETT certification. Tell me more.
Well, actually, we are...
What is OSETT? We're the professionals who design,
maintain, and repair the electronic equipment that makes our world so incredible, and so much more.
We are the experts who make advanced products that touch every aspect of your life.
We are the professionals who help your companies save time and money with our experience and expertise.
We are the professionals that plan, design, and supervise the infrastructure that makes this province and economy successful.
We are the engineering technicians and technologists, the part of a skilled team that builds the community in which you live in.
We are professionals who are passionate about the environment by providing services including sampling, modeling, and assessments, all in an effort to protect this great province of ours.
When can you start?
Thank you. So when you ask, what is OSETT certification? I say we are.
We are.
We are.
We are.
We are.
We are future ready. Our certification?
Your success.
Great. Okay, so I will turn it over to Thierry Vautier. Just a little bit of a background on Thierry. He's been working in North America, Europe, Africa, and Asia, mainly for Caterpillar, before moving to Canada and joining Transpod as the Procurement and Supply Chain Director. He has 2 master's degrees in General Engineering and Business Management from Centrale Lyon and EM Lyon in France. And sounds like he also runs marathons. Maybe I'll pass it over to Thierry now, and he can tell us a little bit more about himself.
Thank you, Albert. I'm not talking about marathons today, but happy to talk about running with any one of you anytime. So yeah, I joined Transpod a few years ago. And today I'm with Dimitri, Kyle, and Augustin. And we have a lot of things to describe you about what we're working on, the company, the technology, the Hyperloop movement in general. And I'll do an overall presentation of the company, our projects, especially our projects in Canada. And Dimitri and Carl will deep more into the technology of the systems. And Augustin is our design director, sorry, and he's working on the passenger experience, the whole design of the systems to make sure it's comfortable and nice to look and efficient at the same time. So Dimitri, you want to say a few words about you quickly before I start?
Yeah, sure. I'm Dmitry. Hello. I'm a Russian nuclear engineer, and I've been living in France for the last 5 years, doing my PhD in plasma guns simulation. And last year I joined Transpod to help them with their simulations too.
Perfect. Kyle, yeah.
Hello. Oh.
Yep.
Okay. Everyone can see and hear me. Yeah. Yeah. So this is Kyle. I work for Transpod doing electromechanical engineering and prototyping, testing out ideas, and I just been building stuff my whole life, and it's fun doing it for these guys too.
Thanks. So it's COVID, so we're all home. I know Augustin is dealing with his kids at the moment, so he'll be back in a few minutes. I'll start with an overall presentation about Transpod. It's the boring administrative stuff, so I'll be short and make sure there's a lot of time for the technical team to share what they are working on. So Transpod. This is, as you could say, one of, next slide, sorry. Yeah, it's we call ourselves a Hyperloop company and a next generation Hyperloop company. Hyperloop, as I think all of you know now, it's another name for tube transportation. The idea is to have very high speed traveling in a low pressure tube, remove the air from the tube so there's less aerodynamic friction. And thanks to magnetic levitation and magnetic propulsion, we're able to reach very high speeds, up to 1,200 kilometers per hour. That's about 700 something miles per hour. It's just below the speed of the sound. And our vision, our mission, you see here, is to be able to transport people and goods at the scale of a country, so between cities at a very high speed and a low cost, of course, and not spending too much energy. climate change is real, it's happening. So we want to make sure we are able to replace airplanes by traveling on the ground. It's safer than being up in the air, and spending less fuel than the aircraft. How does it work? It's an elevated infrastructure. It could be also underground, but it's cheaper to make it above ground, and it's easier also for us to compensate the change of terrain. If there's a small valley, for example, we can extend the height of the pillars. So 2 tubes made of steel, 1 tube for each direction. And inside you have what we call the pods, so high-speed vehicles, about 25 meters long. They can carry 25 to 40 passengers, depending on the number of seats and what we put inside. Augustin will talk more about that. And another nice option about this system is that we can use the infrastructure to put solar panels on top. We need the inside of the tube to have the vehicle circulating, but anything outside of the infrastructure can be used for anything. It could be used as a utility corridor, carry electricity. So the solar panels in an ISD to generate electricity, not to power the system, because, well, of course, when it's raining or at night, then we wouldn't have any electricity, but we can still harvest the power of the sun using the infrastructure. I'm dealing with cats. That's probably what you hear behind me. Briefly, the company was founded about 5.5 years ago now, in 2015, in Toronto. We have operations in Italy and France as well. So Kyle and I are in Toronto, Dimitri is in France, Augustin is working from his home in the Netherlands. And it's global. So a lot of people are asking us, are you building a line in Canada? That's your main market? Well, of course, we're Canadian, so we would love to see a high-speed transport line in Canada, but there's a lot of other opportunity to explore all over the world. So, for example, we've done a feasibility study for a line in Thailand. We're also exploring some other countries, Australia, the Middle East. And in terms of nice progress that we have, I won't spend too much time on that, but we can get back to the Q&A session. We are highly involved in the regulatory work at the French and European level, also a little bit in the US, and we're starting to work on the regulatory projects in Canada as well. What is it for? So I said before, passengers and cargo. So we're not only transporting people from point A to point B or between cities, but we can also make good travel. And that's very important because here we can replace, for example, airplanes between various cities. Same, very high speed. So the idea is to be able to do same-day delivery. E-commerce is booming, especially since COVID started. And what we have as an option today to carry goods from one country to another, from one side of the country to the other side of the country, is the airplane. Because of course we want everything to be delivered right now or later today or tomorrow. So that's how we can solve part of this equation, is by being able to transport cargo at very high speed between places. That's a little bit marketing about Transpod. Why we think, or why we find we are better than the competition, it's because we have a few unique patents that place us above the Hyperloop world. That's the idea of Ryan when he started the company. That's our CTO. He started off a blank page. He didn't think we should start again with existing concepts like the maglev concept, for example. Maglev exists, it works, but it's very expensive. That's why we don't have maglev lines. Well, there's one in China, but that's it. So the whole idea was to think, how do we make something levitate in a tube that's almost vacuum? How do we transmit power to the vehicles? How do we make that happen? And that's how we had some key ideas. Well, Ryan had some key ideas, and some people like Kyle, for example, like putting these ideas, well, literally in motion. But he will tell you more about that. Canada. We would love to build a line between Toronto and Montreal and have a stop in Ottawa. That would be nice. It's a little bit complicated. We're dealing with 2 different provinces. So we're still working on that project. But today, the most advanced project for us in Canada is a line between Calgary and Edmonton. We managed to get the government of Alberta on board with the project, so they're officially supporting us. The first step of the project is to conduct a feasibility study, a preliminary feasibility study. So we have a whole team assessing the costs of the construction, the riderships, goods and passengers, where we could implement stations. We have 2 points only on the map, but really the line is Calgary downtown, Calgary airport, then to Edmonton airport and Edmonton downtown. So we could transport people from city center to city center, and also the people from Edmonton who have to catch a flight from the Calgary airport, for example, where they can hop on the Transpod line. And about 30 minutes later, they're down to Calgary airport and fly off Calgary airport to anywhere they need to go. Part of the feasibility study is also to see if there's there's an interest in having a station in Red Deer. Red Deer is a small city halfway between the two main cities of Alberta, but it comes with a cost. So that's why we're conducting this feasibility study, to see if the line is profitable and if it's interesting to have an additional station in Red Deer, for example. Once we deliver the results of the study, we're targeting spring for this study. Then the next step will be to build a short segment of the line, most probably between Edmonton and Edmonton Airport, validate the technology, have Transport Canada certifying the technology. And then once all of that is working, then we can build the whole line between the two cities. Here, a small example of, that's the first step of the project, the second step of the project in Alberta. That's the test track. That's how it would look like. We need a long test track because, well, it takes time to accelerate. It's not a rocket, so we're not accelerating in 2 seconds from 0 to 1,000 kilometers per hour. So it takes a few kilometers, which is why we need a long portion of land. And actually, Highway 2 between Edmonton and Calgary is perfect for that. It's straight and it's flat. So that's the roadmap. Not spending too much time on that, but just the idea of this slide is to show you that it's a very long project. I joined the company in 2016, at the end of 2016, and one of my first questions was, so when do we start digging a hole and putting some pillars in the ground? And we quickly realized, well, no, this is going to take a few years. So the main milestones for us is 23, 24. It's to have the certification for the transportation system in Canada. And then we can start building the test track. Finally, we can start building the line. And so right now we are hoping to be able to operate the line in 2031. So about 10 years from now. So that's it for the overall presentation of the company. Any question you might have, you can either ask them in the chat. Make sure you put your email address with your question. So if we don't have time to get to all the questions, then we have your email address and we can get back to you by email. And there's going to be some time for Q&A live as well. So put your questions in the chat and or ask the question at the end after all the presentations. Augustin, you're next. Right.
Hi, so let me present you this. All right. So can you all see the screen? Yeah.
Yeah.
Good. So hello, I'm Augustin. I'm industrial designer. I'm the director of design, and I will present you what design brings to Transpod. So I'm 39. I'm from France, and I live in the Netherlands, as said Thierry. I have a lot of experience in transportation industries. I started with car design for Jaguar, and then I quickly moved to railway industry. I joined the company Alstom, where I designed trains for 15 years. I designed metros, tramways, mainline trains, and high-speed trains. I also designed freight locomotives. It was great to create vehicles for various locations in the world. So, not only the exterior, I spent also a lot of time creating their interiors. From economy to business class, I learned a lot on how people move and on what could be done to improve their experience. However, I had to work within the limits of a system shaped for centuries. There are a lot of limitations that can't be overcome due to the existing infrastructures, the technical constraints, the regulations, restrictions, etc. So then last year I joined Transpod, where everything is possible, where you can change everything for the best. So here is how design works. First, we analyze the current situation and people's needs and their expectations by observing them, making analysis. How will people live in the future? How will they move? How do they want to move from the point A to the point Z? And how can we make sure that our product will match their needs in terms of travel? The goal is to make sure that our solution will be more than simply a faster way of moving, but also a better way of moving. So we also create scenarios where we try to imagine all the passengers type going through any kind of situations to make sure we improve the way people travel. We had in mind all the inconveniences we can meet when we use trains and planes to make sure we solve them. We keep a holistic point of view, the tangible part, the digital part, the infrastructure, the vehicle, the other modes of transportation that are connected to, etc. You know, we try to map everything to make sure we have the best overview when we create solutions. So from that analysis, we start conceptualizing and shaping our ideas. It's hundreds and hundreds of ideas that are shaped, simply using at the beginning a pen on a paper at the beginning. We integrate step by step all the engineering inputs provided by my colleagues. Everything that we got from the previous analysis, of course, is central. And the goal is to create a product that is the best solution. And especially, this is the industrial designer goal, is to create a product from the user perspective. That's what we really try to solve. So it's also important as well to give it an inspiring look that carries its functions. It has to show its function and communicates its value, as well as the company's value. For the interiors, the process is the same. We have a greater focus on the passenger experience. We first need to develop the most optimized architecture that will allow a high level of personalization to meet all the different needs, the various type, the future type of travels. We want to make sure that even when the system will be saturated of passengers, the experience will still be superior to what is already existing. Of course, everything here is still preliminary work, but it's going on step by step. So after the sketches come the 3D modeling step, where we define more precisely the different aspects of the vehicle. We put together all the engineering inputs and check how it works, and try to keep the vision alive. Sorry?
Très intéressant. Regarde.
So, yes, so we can also create then more realistic images, which are very useful for our partners and our future users to understand what we plan to do. Therefore, we can get some feedback from them and improve our vision for the next iteration. And yeah, and coming soon to your place. Thank you.
Thank you, Augustin. Dmitry?
Hello. Gonna start sharing my screen in a moment. Sorry for a short delay. Okay. So in my part of the talk, I'm going to talk about numerical modeling and simulations. It's slightly another flavor of modeling in comparison to the type of modeling Augustin does. First, I will tell you about the terminology I'm using. Then I'll explain the algorithm we follow when we want to create a model of something, some process. And in the end, I will give you a few examples from my practice. So the base notion of my field is a model. And in my case, it means a simplified reflection of reality. And if we talk about model in a scientific sense, it's a process of creating a model. And finally, a simulation is an approximate imitation of a process. So basically, how a model behaves in time. The major goal of numerical modeling and simulation is to predict the future. And there are multiple ways of approaching this problem. For example, on the bottom left, you can see a model built on physical analogy, where a gravitational field is represented by a piece of cloth. Then there are models built based on scaled down versions of things we want to model. Like here in the middle, there's a transport vehicle, scaled down version of it, that's being exposed to airflow inside the tube. And on the bottom right, we have numerical models that are fully inside a computer. Numerical models could be roughly split into three categories based on their degree of realism and the computational power required. And the left part of the spectrum, we have video games that are the least realistic in a physical sense, but they can run in real time, so they don't require overpowered computers. In the middle, we have visual effects and computer graphics. Here, the goal is to make it look realistic, but we do not necessarily need realistic physics. Thus, we require more computational power and like days and months of computations to produce these pictures. And on the right part of spectrum, we have modeling for engineering and scientific purposes. These kind of models, they could be potentially the most advanced, but in the worst case, they can require from days to months or to even years of simulation time. But regardless whether you'd like to make a video game engine or if you'd like to simulate a vector training, you're likely to follow the same algorithm. First, you gotta formulate the problem you'd like to solve. Then you should analyze the physical nature of this problem. Next, you should describe physics using mathematical apparatus. On the next stage, you have to interpret this mathematics to computer, so to write in a form that computer understands, so basically by writing a computer program. And then you have to use this computer program to solve the initial problem. So now let me show you how is it done based on the tasks we have in Transpod. So here is a simple example about prediction of the tube surface temperature when it's exposed to direct sunlight. So I received this task because our engineers needed to estimate the maximal temperatures of the tube and also to see whether they should paint the tube or if it's good in unpainted state. So the first thing I did, I analyzed the nature of the problem. So here are approximate representations of the two tubes. Here's the sun and the sunlight that is hitting the tube surface. Let's consider a small segment of the surface and see what happens here. So we have sunlight that arrives to the surface. Part of it is reflected. Another part is absorbed. The absorbed part hits the surface. So it's an energy gain. At the same time, the same piece of tube loses energy due to heat exchange with the surrounding air by convection and also by thermal radiation. So this forms energy loss. And the resulting the tube surface temperature could be found within this balance. So if we write well-known physical laws that describe these processes, we can get such a balance equation. I won't be describing you every letter here. All you have to know is that there is only one unknown here, is the surface temperature. And it's up to us to solve it and to find the result. So for this, we need to write some code. So if we make some simple transformations and move all the unknowns of this equation to the left and everything we know on the right, we will get something like this. It's a quadratic equation that can be solved graphically by finding the intersection between this curve and this constant level, like here. And it could be done using a simple algorithm, simple for or while cycles in any programming language. So once I wrote this simple program, I was able to predict what are the expected temperatures along the tube circumference. As you can see, in the unpainted case, it's around 50 degrees, while applying white painting reduces this temperature almost by 30 degrees. So the answer to the engineers was that indeed, it's better to apply some coatings or some painting. Similar mathematics is used in computer graphics to simulate how light reflects from surfaces. Now, let me show you a more complicated example, really briefly. And it's the main thing I do in Transpod. It's about fluid dynamics or hydrodynamics or aerodynamics. Let's consider a pod that moves inside the tube with a high velocity. When it moves, it displaces the air. So the air has to squeeze through this gap, and while squeezing, it accelerates to high velocities as well. And it appears that the velocity of the air that squeezes in this gap is limited, and this limit is the speed of sound. And this creates a problem because it limits the maximal speed our vehicle can reach. So the question we wanted to find the answer to was whether it is possible to reach 1,000 kilometers per hour, as it's a big marketing point for our vehicle. And in order to do so, we have to solve this fancy system of equations, with these three being the most important ones. These are equations that describe air velocity, and they're called Navier-Stokes equations. Believe me, this system of equations is as scary for me as it is for you. So usually we skip coding part, and we just buy pieces of software that are capable of solving it. So all we have to do is just to build a 3D model of the pod and of the tube and make the code do its work. So here are some of the results. I can briefly explain what's happening here. On the bottom left, you can see the pressure fields. So when the vehicle moves from left to right, it compresses the air in front of it. Sudden compression causes heating of the air, as you can see on this picture, where the air in front of the vehicle is quite hot. Well, it's about 100 degrees Celsius, which is good because in hot air, the sonic speed is faster. And so it's about 400 kilometers per hour. On the right picture, you can see the air velocity. And in this gap, as you can see, it's around 300 meters per second. Thus, by comparing this 300 with the sonic speed, which is 400, we've proven that indeed there is no limit so far, and our vehicle could indeed reach 1,000 kilometers per hour, or maybe even more. Navier-Stokes equations are rather heavy, and usually they cannot be solved in real time, but now due to advances in computers, some real-time simulations are possible, and now there are even some games that solve these equations. Like you can see on the left, there's cloud simulation using Navier-Stokes equations, and on the right there is some smoke simulation. Okay, thank you for your attention, and now Kyle will tell you about mechatronics and hands-on approach. Thank you.
Oh, there we go. Can you hear me?
Yep.
Okay, there we go. All right. Hi. So yeah, the hands-on approach. I do electromechanical prototyping and hands-on experiments, just practical, let's see if it works or how it behaves type stuff. I've been doing that all my life, and now I'm doing it with Transpod. So the vehicle, traveling at high speed down this tube with almost all the air evacuated, kind of floats on a magnetic field, or I like to think of it as it kind of surfs on a wave of electromagnetism. So what does that all mean? Well, kind of like a maglev train, we're using magnetic fields to have a system where there's no contact between the vehicle and the tube, and that's where a lot of the efficiency comes from. The air being gone, so there's no air friction, but also if you're not in contact with a road or a track or a rail or anything else, you don't lose energy to that either. So how do you make something float with a magnet, right? Like if you take a magnet and put it close to something that you know it'll kind of stick to, it just jumps right for the rail. There's not really a sweet spot where you can keep that magnet and it will just float there. It always wants to run off on you. So, okay, what if I have a magnet where I can adjust its strength? Kind of like, you know, maybe at home or following a YouTube video or even in science class, maybe you've built one of these. It's just some wire wrapped around a nail. And if you touch these wires to either side of a battery, you get a electromagnet. You can pick up paper clips and stuff. And there's all kinds of different forms that you can build these into, depending on what you're trying to achieve. So this is another electromagnet I have. And it is hooked up to a adjustable power supply. So it's like, all right, if adjusting the distance doesn't work, what if we adjust the strength of the magnet? So I'll put the mic down and I'll see if I can get this magnet to float here by adjusting how much power we give it. And I could keep doing that for the next hour. Still same problem. It won't hover there. It's always going to want to stick or fall. So what we need in addition to an adjustable magnet like an electromagnet is we need a control loop and a sensor. So what that means is we need a way to measure how far that magnet is away from our rail and adjust how much power it gets really, really quickly. So that's kind of like when you're in the shower, setting the temperature for the shower and the water's too hot. You close off the hot water tap until, oh, it's a little too cold now. And then you open it a little bit. Now that's a little too warm. And you close it. You keep kind of adjusting until you hit that sweet spot. And then someone upstairs starts to have a shower and it starts to get cold again and you have to adjust it again. But the idea is you're taking a measurement with your hand or your sensor, thinking about what needs to happen, making a decision, and then affecting. You turn that tap to adjust how much hot water you get. So here I have a setup that does something like this, but it does it with sensors and electromagnets. So on the ends of this apparatus, I have two little sensors, which are kind of like eyes or fingers or something like that, they're specially designed to detect exactly how far away they are from a piece of metal. You actually might be able to see on the scope back there that purple line jumping up and down. So that's the output from the sensor. That's telling our computer exactly how far away we are from the rail. So and adjusting how much power the magnet gets. So if I bring this up here, I have to balance it on one end. There we go. And it actually hovers just below the rail because it's taking a measurement, making a decision, and affecting the output so quickly that it can actually make it float. So in this case, it's actually making a measurement, making a decision, and changing the output 5,000 times a second, which is pretty quick. That's a lot of processing happening really quickly. On the full-size vehicle, on the big vehicle, going at really high speed, ripping down that pipe, we'll actually be taking measurements at least 30,000 times a second. So at that top speed, that means we're still measuring how close the limbs of the vehicle are to the rails every couple millimeters. Even if it's traveling 1,000 kilometers an hour, we still check where is it positioned every couple millimeters. So that's one of the things I've been working with lately. We've been testing these sensors to make sure that they do their job reliably and consistently. They don't drift. And that's where simulation can't quite do it. You've just got to grab a wrench and a drill and whack some stuff together and try it and test it and see. Simulation gives you a wonderful kind of head start. It gives you a direction to go in. It can save you some time giving you estimates, but to really know how a system's going to behave, you got to try it. You got to build it. And yeah, that's what I do for us. So yeah, we're kind of reinventing magnetic levitation for trains, as Thierry said, where we've looked at how typical maglev systems work, and they're somewhat like this, and what we're doing is somewhat like this, but we're reinventing it to make it cheaper, more efficient, and nice and safe as well. So that's my bit. Thank you very much.
Thank you, Kyle. Yeah. Okay, so this is in a nutshell, as short as we can, an overview of Transpod, our activities, who we are, and what we do. Albert, I don't know if you have anything to say right now, or if not, we can jump to the questions.
I think jumping to the questions are to find a choice, and then following that, I'll give a brief, I guess, closing remarks, and I believe there's a poll afterwards as well.
Yeah, okay, perfect. I'll start with a question in the chats. I know Kyle has answered a few about safety regulations. So regarding the fact that there's no air in the tube, so Kyle, you want to explain a little bit more about that?
Yeah, we are spending a lot of time making sure, as a lot of people pointed out, yeah, there's a safety concern with having a vacuum in a pipe, or near vacuum anyway. We're not hard vacuum. We have a little bit of pressure in there, which makes certain things easier. But yeah, we're spending a lot of time talking to experts, talking to, or at least using information from things like NASA and other space programs, any experience that we can find with vacuum systems. We're carefully working with materials engineers and doing simulations to make sure the pipe is safe and strong. We're investing a lot of time in coming up with standards and collaborating with many companies to make sure that, yeah, everything is as safe as possible. Yeah, that's most of what I could say on that.
Yeah, something to add on that is that it's finally more, when we say it's safer than an airplane, it seems very safe to fly today, even though there's a few accidents, touching wood right now. But when anything happens in an airplane, you're 30,000 feet above the ground, and there's literally no escape. When you're in a vacuum tube, a Hyperloop or a Transpod line, we have safety systems that allows us to repressurize the tube in a few dozens of seconds. So we make sure that nothing would happen to you. And once the vehicle has stopped, the atmospheric pressure is back in the tube, then you can just safely exit the pod and go to the next exit of the tube, and then you're safe on the ground. There was a question from Mahai. I'm sorry about the name, Elia Maha. Why not having one connecting the sides of Ontario? Well, there's a lot of sites and corners in Ontario. There's one project that is connecting Windsor to Toronto. It's part of the whole line, Toronto, Ottawa, Montreal, Quebec City. South, it would go to Windsor, hopefully to the other side, Detroit, and then the lines could go to the US. It's a matter of how many people we would transport, passengers, and how much freight we can carry. If there's not enough people, then there's not enough revenue, and it's not profitable to build the line. So there's two things. The line should be built because it's good for the people, it's good for allowing people to travel. But at one point, someone has to pay for that. And when we talk about some $1 billion, well, the people who will invest these $1 billion, they want to have a nice return on investment. And as much as we would like to have lines connecting the whole Canada, well, we need to find money to build that. That's why we are working on this project. It's advancing slowly, not as fast as the one in Alberta, but that's part of the plan. There's a question about the test track in Dreux in France from Raoul. I recognize your name. I think we've changed a few emails here and there. Good to see you, by the way. Well, COVID stopped a few projects in France, or so put on pause a few projects, but it's still on track. We're designing the line as we speak. So we have a French partner called SAD that's designing everything from the pillar, tube, dimension, thickness, the expansion joints. So right now, the first step is to design the line, and then we'll move to construction. Ideally, we will start to dig some holes in the ground this year, but it's all related to how fast we can move in the development. Another question about the simulation programs we are using. So Kyle, you answer to that. ANSYS, OpenFOAM, Fusion. We work a lot with Autodesk, it's true. We are starting to work with Siemens and X as well. It's not for simulation, but it's like a whole suite of program that helps designing an aerospace project. And can you speak to other competitors in this space and their differences? We are about six or seven, I would say, major companies working on Hyperloop developments at the moment. So there are two in the US, Virgin Hyperloop and HTT, Hyperloop Transportation Technologies. So they are working on similar projects than the one we are working on with different technologies. It's like when you have a car, there are several ways to make the car run. So you have electric cars, diesel cars, gasoline cars. You can have the engine in different configurations at the front, at the back. The safety systems are different. So that's about the same, slight difference between our different companies. We're all trying to make the whole technology happen. I'm not saying the first one will be the main one or the best one. There's room for a lot of companies in this area. So the most advanced project today is Virgin Hyperloop project. I'm part of Transpod, so I'm biased. I'm not saying their technology is the best. I think our technology is better, but that's up to anyone to study the documents and make their own decisions. And there's also a few companies in Europe. So there's one in the Netherlands, one in Switzerland, one in Spain, and the last one in Poland. So right now, the research and developments are focused in North America, Europe, and there's one government lab in South Korea that's also working on the technology. But the main issue, as for any development of this size, is the money. It requires a lot of money to make the whole technology happen. And so we are all working as fast as we can according to the funding that we get. And going under the oceans, anyone want to talk about that one? Or I can. I mean, long story short, no. Mainly because, well, you're traveling at 1,000 kilometers per hour in a tube. So any slight movement of the tube can be or could be catastrophic. And it's vacuum. So there's a lot of pressure on the outside against the inside pressure. If you add the pressure of the water, that's even stronger. So it's, well, technology speaking, it's too complicated today to make that work under the water. As a tunnel or below or inside a lake, why not? But the ocean with the waves and everything, it's not for now. Anyone else for the next question? Kyle, I think you want to answer the next one.
Let's see. Well, okay. Yeah, speed concerns. Let's see. Wouldn't half the speed or 600 kilometers an hour be more efficient, safer, or more practical? There are stretches of route we're actually looking at having lower speeds, just because of practicalities with acceleration and deceleration time and all of this. So, I mean, in certain ways, yeah, there's certain places that running at lower speed is going to be safe, but where there is the straightness and the time to spare, basically, for acceleration and deceleration, we can hit those higher speeds without really consuming that much more power. Again, because it's so close to vacuum in there, really getting up to higher and higher speeds is mostly just power over time. You don't need to put way more energy in to go a bit faster. It's a bit more energy to go a bit faster, put simply. But yeah, you're right. Certain routes would actually run a little bit slower just because of practicality.
Yeah, and when we say 1200, or when I say 1200 kilometers per hour, it's a maximum speed. It doesn't say that it's going to go that fast like 100% of the time. So yes, right, it takes time to accelerate and then at the end to decelerate. But also when there's a curve, we have a design that's able to handle tight curves at very high speed. But if there's, like, for example, a mountain and we can't go through the mountain for whatever reason and we have to go around and there's a very tight curve, then we may have to decelerate as a train would do. That's very similar. Or when you're driving a car and there's a tight curve where you have to slow down, it's very similar to us. So we say 1200 kilometers per hour as a maximum speed, and cruise speed or average speed would be more like 800, 900, maybe 1000 kilometers per hour. Question about magnets for you as well.
Right. Okay. Yeah. So we have it's a multi-magnet system. So we have magnets for lift, for thrust, and we are experimenting kind of with some combo systems that can actually do like lift, thrust, and like using repulsion, using attraction, using a bunch of different schemes kind of combined. But yeah, one way to think of it is yeah, there are magnets on there for levitation, and that may do combo duty thrust, and then there's separate magnets that really do thrust, and that's their job.
Okay. Well, if there's no other question, Albert, I think it's back to you. Yeah.
Sure. I just have one last question. You may recognize it. I understand there are some high school students participating today, so I thought if you could just speak to your education backgrounds and sort of what they need to do in the event that they wanted to pursue in your footsteps.
Okay, that's going to be a question for Kyle and Dimitri then.
Oh, I could say that to pursue modeling stuff, well, study physics, study mathematics, and study programming. Apply for university or do it yourself. There are a lot of online courses. And yeah, be determined.
And yeah, I would say the same thing as well. If you're interested in any of this stuff, try it now. Grab some wire, grab some batteries, borrow someone's old computer, write code on it, whatever it is. Don't wait for, I'm gonna write awesome software once I take that programming course. No. Try now, make mistakes. I started building things when I was about 5 years old. And I made a lot of mistakes. I blew up a lot of batteries. I blew up a lot of parts and broke motors. And But you know, I didn't start any fires that my parents couldn't put out. Um, but yeah, it's just start, try, and of course, yeah, math, programming, all of that stuff is really important. You need your math. You'll use your math every day when you're doing engineering, even if it's stuff by feel, even if you're just hitting things with a wrench and greasing things. You will still need math. It's a big one, and English too. Don't shy away from being able to write and communicate, because you have to be able to communicate with your team. Yeah, that's most of my advice.
Yep, I agree. The first years of my engineering school are a lot of theory, not a lot of practice. And so it's, well, of course, super complicated and not very interesting, but it's necessary. That's the math part. And we did a quick poll in the classroom, and we realized more than half of the classroom was playing with blocks when they were kids. So that's back to what Kyle said, like, yeah, try, play with stuff, build stuff, make sure you start a fire when you're at home and not at the office. But yeah, and yeah, most important, have fun.
There's one more question there.
Yeah, thickness of the tube, 2.5. That's what we're aiming for. Well, it could be 2.5 or half of it. Whereas there's room to play between, it's about an inch, so half an inch to 1 inch. And Albert, if I can, last question, very last question. So power backups, redundancies. Yes, of course, Kyle can talk about redundancies.
Oh yes, yeah. There are several power redundancies in the vehicle, both for kind of like really high instantaneous power and for stuff that will run for hours if we need to keep, you know, we should be able to, yeah, we'll have life support systems for hours, lights on, all that kind of stuff in no problem. But for really high power, for levitation and thrust and all that other stuff, yeah, we have backup systems kind of at all sorts of different levels. There's many redundancies.
Yeah, in case there's no power anymore in the system, well, there's like an emergency landing system, so
Yeah.
wheels on which the pod can land and roll safely until it stops. And then, well, as I said before, we put back the pressure in the tube. We open the doors of the pods. We open the doors of the tubes. There's going to be doors every kilometer, every 2 kilometers. It's part of the negotiations or discussions we're having with the regulatory bodies. But it's similar to a tunnel. Just imagine like you were driving into a tunnel. If you're stuck in the tunnel, there's every 750 meters, every 1 kilometer, there's a safety escape on the side of the tunnel, and then a safety tunnel from which you can escape, well, whatever infrastructure you're in. So it's going to be very similar. Of course, then, well, you're in the countryside somewhere, as if the train stops between Toronto and Montreal, and we are all stuck in Kingston, but it's a nice place to visit. And when local people will see something in Drew, hopefully before the end of the year, when we can start clearing the ground and starting to dig foundation. But I'll get back to you on the exact date because I'm not sure about the planning for that.
Great. Well, with that, I think we'll conclude the session. Thierry, thank you so much to you and your colleagues, Dimitri, Kyle, Augustin. Great presentation as always. It's very informative, very interesting. Just want to have a shout out and thanks to Lawrence from the Renfrew chapter of OSETT for helping coordinate this presentation today. Before everyone leaves, there's a poll. I think it just popped up. If you could just participate in that poll, it would be greatly appreciated. And thanks again for attending.
Thank you all. Thank you, Albert.